Okay, next comes division. So division is going to be way more complicated and actually a lot harder than multiplication. Just fair warning. So in the division, you have your quotient, your dividend. You have your divisor, your dividend, and then your quotient. So remember, the quotient is your answer as well as your remainder. So now again, just like multiply, you have two answers at the end. Remember, we're doing integer division, not a decimal point. So we're going to have the actual quotient up top, which is the answer to the division, and the remainder, which is what's left over. By the way, in case it was never clear, when you do division, you get this number. When you do modulus, you get the remainder. So notice that both divide and modulus are the same operation. You have to go through the same steps. So in the long division, we have our dividend, we have our divisor. We wait until we're looking at a big enough dividend in order to do it. So we subtract right here 1,000, bring down the 10. Notice we put the 1 right here. And hopefully this is still the way they taught division. Bring down the next digit, bring down the next digit, and then bring down the next digit. Okay, it's greater than or equal to our divisor, so let's subtract the divisor, add that 1, and then since we're at the end of the dividend, what's left over is the remainder. Okay, and that's basically what we're going to do here. So the divisor, again, a little complicated as well. But look again, there's a 64-bit ALU, so you know what question I'm going to ask in a moment. But here we go, the divisor. Notice the divisor is in the upper half, and the dividend, the remainder is initially the dividend. So remember, the divisor, because we get their names wrong, is this number over here. The dividend's what you're subtracting from. How about that? And your quotient is the answer to the division question, and the remainder is the answer to the modulus question. Alright, so the dividend is the big number, the divisor, which is on the left half right here, and then the quotient, which is, again, what's on top. Okay, so the quotient, by the way, is going to be the answer. So we start off with the dividend right here. Notice that it is what goes to the control test, because you're testing if what you're looking at is big enough to be, where is it? Divided by the divisor. And if it is, then it does the subtraction. Now let's go and look over here, because this is going to get really complicated. So we subtract the divisor register from the remainder register and place the result in the remainder register. So notice that right off the bat, we're just going to go ahead and do the subtraction. That means that when we're looking at 1, just 1, we're going to do 1 minus 1,000. Now hold on, if the remainder is greater than 0, then that means that we're keeping this answer. So we'll shift the quotient to the left and setting the newmost bit to 1. That means we can do the subtraction. Otherwise, the remainder is less than 0. What that means is that we subtracted too large of a number. So we restored the original by adding the divisor register back to the remainder. Yes, that's confusing, but what you have to understand is that the computer has to decide, or we have to find out programmatically, if this one is greater than that one. How do we do that? Well, the common way to do it is to actually just do the subtraction, and if it's your negative number, then you just add it back. And then once you've added it back, just shift the quotient register to the left, making that last digit 0 because you can't subtract that yet. Then you shift the divisor to the right by 1 bit, and then we are good. Notice that this is the divisor. By the way, the divisor is in the upper half, which means that the beginning is way bigger than that entire number. What might be helpful is if you saw that this had a ton of zeros, and then we're going to slowly peel off each 0 until we get to a number that's big enough. So when we're actually doing this subtraction, we're actually subtracting with those extra zeros right there. And then we're going to repeat this 33 times in order to get the final answer. Alright guys, you're probably going to need to sit down and stare at this one for a while because it is not that intuitive. A couple of things to keep in mind while trying to decipher what's going on here. keep in mind that divisor is in the upper half, so it immediately has extra bits on it. So if it's in this example, we're doing a 32-bit division, so the first thing that happens is the divisor goes in the upper half, and so therefore it has 32 zeros on the right half. But the remainder is the actual answer, and so if you're doing 32-bit division, you're not going to be able to do much right off the bat, because obviously the divisor's in the upper half and the remainder's in the lower half. That's how it is. And then as you shift things, you'll start to get answers to pop out. So again, make sure you put the divisor in the upper half and just add a bunch of zeros effectively when you're doing your division. Keep in mind that the ALU is subtracting and adding back, and then the quotient is simply being shifted to the left. When you are done, the answer to the division is in the quotient, and the remainder is what's answer for modulus. All right, optimized. This gets a little more confusing. Actually, it gets a lot more confusing. Looks a lot like a multiplier. That's because it kind of is, and what's nice is you can actually use the same hardware for both. Well, that's convenient. So in this one, notice again the divisor is 32-bit, the ALU is 32-bit, and you do not shift the divisor. So just like the multiply, the multiplicand was 32-bit, now the divisor is 32-bit, and there's no shifting on the multiplicand or the divisor. And also the ALU is down to 32 bits. Notice also the ALU is only going to operate on the top half of the remainder. And how these slides don't tell you where they're putting the remainder initially. All right, so let's go at least look at this a little bit. Hopefully that'll make sense, because notice that you're shifting some things to the right and some things to the left, which is confusing. So notice here the divisor was being shifted to the right and the quotient was being shifted to the left. So, whoops, the divisor is being shifted, let's see, and then I think in this answer it's actually going to be backwards. So the quotient is actually going to start, well, we want the remainder, hold on a second. So the remainder is still the 32 bits, and we want that to be on the right. And so the quotient is going to be over here on the left, and we're going to shift it up. So the idea is that the divisor is going to be here. Go to the control test to see if we can do the subtraction with the divisor, and if we're allowed to, because the ALU is going to go back to the control test and tell you if the number is positive or negative, and that's where the control will tell you to either keep it or restore it. And so you put your divisor, let me make sure I did that right. Good. Divisor's up top, and the dividend's right here. Great. So the dividend starts here, and it'll be shifted to the right as needed, and then 32-bit ALU, which we'll put it up here. So please go through a couple examples here. I really wish I had the board. All right, with faster division, can't use parallel hardware as a multiplier. Why is that the case? Because if you go back and you look at the division flow graph, a test has to be done right here if the remainder is greater than 0 or less than 0. Because of that, you can't just pipeline and push all the numbers through. In the multiplier, we didn't have the decision right there, so you can just push multiplication straight through. But here, since we need to decide whether we're allowed to do the division or not, that means any future repetitions actually depend on the previous one, because the previous one's going to set whether the bit is 1 or 0. So therefore, you can't just pipeline it with multiplication. So the divisions on here actually get very, very complicated. There's some fast dividers called SRT that generate multiple quotient bits per step, but they still require multiple bits. The idea with SRT is that they're basically going to memorize the answers to like 4-bit divisions and then store those in a table, and then that way it'll use those table lookups in order to optimize certain divisions. Unfortunately, that gets very complicated, so we're not going to go over that, but do realize that division is actually a very difficult operation for a computer. All right, next, we're still going to talk about MIPS division. So just like with multiply, it's the same idea. You'll have a division, and then you'll have the high and the low in order to access the results. So the high will be the remainder and the low will be the quotient, aka for modulus is high, for the regular division it's low. Alright, next we're going to talk about floating point, but I'm going to save that for next class because I think trying to get division and multiplication done right now will be plenty of work. So let me pause for a moment.